I have a question about the lab number 4.
Okay.
So for the table, I just
Mm-hmm.
want to clarify, so when we put in the solution, like I just want to clarify what the initial is just like how much we started out with, so like 0.01 molar of the solution. That would be our initial. If we put in
Wait a minute.
10,
Number 4. That's um, the
there's like,
arsenate lab or the coefficients
yeah,
lab.
I think the coefficient one.
Oh, so A, B, C, and D. You mean?
Yeah.
Oh, okay. Yeah. So basically, the chart would be, how many milliliters of A, B, C, and D you added. What was the concentrations, the molar concentrations of each one? So if you added 10, 10, 10, and 10, the molar concentrations, if nothing happened, should be 0.25, 0.25 all the way across, right? But then if there's a reaction, these concentrations should change. So I don't know what your particular concentration was, but if, let's say, so if A went to 0 and B went to 1.25 and C went to 0.375 and D went to 0.5, then we would know that 0.25 molar A was consumed, 0.125 molar B was consumed, 0.125 molar C was produced. So that went down, this went down. C went up, and 0.25 molar D was produced, right?
Yeah.
Is that what you mean?
Yeah. So like we don't need to solve for like the initial, like the initial is just how much we put initially, right? Or
Yeah.
like,
Well, yeah, obviously you need to solve for that because you don't know when the reaction takes place. You need to know what the initial concentration should have been. So when they react, you'll know that, oh, this is less than expected. So that's a reactant. This is less than expected. So that's a reactant. This is more than expected. So that's a product. And this is more than expected. So that's a product as well.
okay. Thank you.
Yeah, and then at the end, you should basically, based on these concentrations, you figure out which one's the reactants, which one's the products. So then your final on the table, your final reaction should be just enough A and just enough B with no C and D present, so that when you add them together, there's no products at the beginning, and when you add them together, there's no reactants left at the end. And then that will tell you exactly the ratio of A and B that gives you the ratio of C and D that you see. And then you'll figure out, oh, right, it must be 2A and 1B gives me 1C and 2D, something like that. Okay?
Okay. Thank you.
All right, no worries. Oops. Put that back up. Okay. So any questions on this particular recitation? I sort of, threatened or promised, depending how you look at it, that we'd be doing more of these Lewis dot structures and then we're going to start tonight in the lecture to learn about how these Lewis structures turn into shapes, how we can just look at a Lewis structure and convert that into a shape that makes sense. So we'll do a little bit of that this afternoon, and we'll do more of it tonight. So was that a question I heard in the background?
Start with first question, just to get idea?
Well, this is something that we haven't done yet, but I will show you basically how it works. We're going to talk about it tonight.
Okay.
Because we.
If you want, you can skip and go another question.
No, I'll start here. I'll just basically show, because it'll be an introduction as to what we're going to learn, because it's a good exercise for figuring out how you take just something with dots and then turn that into a picture, and then turn that picture into a shape. So we can take one and go all the way through. So let's look at, I don't know, let's just look at sulfur trioxide. Just look at the first one. So how many valence electrons total are there in sulfur trioxide? So we need to look, how many in sulfur? Now for these, it's really helpful to have a periodic table in front of you. Because as I've been harping along, if you don't have a periodic table, you don't know anything. Periodic table tells you everything you need to know with just a few exceptions. So the periodic table will tell you this. Just by looking at the periodic table, you will see how many valence electrons an element has. So what group? Sulfur and oxygen are actually in the same group. Which group is it?
Group 6.
Mm-hmm. That's your periodic table may say group 16, but actually you can just read that as 6 because groups 3 through 12 basically are transition metals, and so they vary, as we know, the number of valence electrons they can have. So 13, 14, 15, 16, 17, you can just look at them as 3, 4, 5, 6, and 7. So since sulfur and oxygen are both in group 6, what's the total number of valence electrons we should have here?
$24.
That is correct. I like how you said that with confidence. Yes, 24. So we have 24 valence electrons. And we have 4 atoms. So one of them is going to have to go in the middle.
So,
Now,
Professor, just I want to ask, how she knows 24? I know it's group 6, so she multiply by...
Group 6. How many valence electrons do elements in group 6 have?
Okay, 4.
6.
Okay.
That's why it's group 6. And
Okay.
there's 4 of them, so 24. Yep. Group 5 elements have 5 valence electrons. Group 7 elements have 7. That's why they're in that particular group. So it makes it easy to. That's why you don't have to memorize all this stuff. Just have a periodic table in front of you. Bing, it's right there.
Yeah, I know group 6. Then how she knows the valence, the number of electron is 24?
Because there's 4
Mm-hmm.
elements here. They're all in group 6. So each one of them will have 6 valence electrons.
Okay, got you.
For a total of 24.
Okay, got you.
Yep. Okay. So which of those elements is going to go in the middle? What are our rules for putting things in the middle?
Sulfur.
Yes, it's going to be sulfur. Why is that?
It's the one closest to the left. And it's on more.
So, right. So if it's further to the left, actually it's not further to the left, it's further down. It's further down in the periodic table. And because it's further down in the periodic table, what does that mean about its electronegativity? As the atoms get bigger and bigger as we go down in a group, what happens to the electronegativity? I mean, think about what electronegativity means, the ability of a nucleus to pull electrons to itself. So what's that ability as the electron cloud gets bigger and bigger and bigger? Does your electronegativity go up as it gets bigger, or does it go down? Your ability to pull the electrons close to yourself. Just think, is it easier to pull electrons that are close to you, or is it harder to pull electrons that are farther from you? So electronegativity means you're able to pull electrons tight. Now, does that ability get less as the atom gets bigger, or does it get more? Man, I'm going to have to ask this in a lot of different ways. Okay, let's look. Fluorine and iodine are both in group 7. They're both halogens, so they have high electronegativities. Fluorine is a lot smaller than iodine. Fluorine only has 9 protons and electrons, while iodine has 53. Which one is more electronegative?
Fluorine.
Fluorine's a lot more electronegative. So electronegative actually gets bigger as the atom gets smaller, because it's much easier for the nucleus to pull electrons close to itself when they're already close. When they're really, really far away, the influence of the nucleus on electrons that are like in shell number 5, so they're really, really far, is much less than with fluorine, because it only has shell 1 and 2. That's it. It stops at shell 2. So n equals 2 here, but n equals 5 here. So these electrons in iodine are much further away. And so the electronegativity of iodine is a lot lower than it is for fluorine. So if you look at sulfur and oxygen, which one's bigger?
Oxygen.
Nope. Look at the periodic table.
Sulfur is bigger.
Sulfur's bigger. Sulfur's one further down. And remember, every time we go down one in the periodic table, we've added a new shell. So oxygen just has n equals 1 and n equals 2. So it just has 2 shells. Sulfur's got 3. So those electrons are now further away, where the nucleus can't pull them as closely as oxygen can. So oxygen's electronegativity is higher than sulfur. So when we want to pick an atom to put in the middle of a molecule, which one do we normally pick? Do we normally pick the one with high electronegativity or with low electronegativity?
With low electronegativity.
One that's lower. And the other reason we generally pick, so usually we pick the one that has a lower electronegativity. We also tend to pick the element that's larger. Not always, but a lot of time we pick the element that's larger because it can generally form more bonds. So we'll see here what that means. So we'll put sulfur in the middle. Oops, got my erase on. I'm going to put sulfur in the middle and then have 1, 2, 3 oxygens. Remember, and then we put 1, 2, 3 bonds on each one. Okay.
Is this where you want us to put it in the Lewis structure box?
Yes. Mm-hmm. Oh. Yeah, we go in the Lewis structure box. So I have 24 electrons. How many to put in this particular diagram? How many do I have left to put in? I put in 3 bonds, so how many electrons do I have left?
1.
1 electron left? How many have I used by making, I've made 3 bonds. So remember,
You used 6,
And
so
if-
you have 18 left.
so 1, 2, 3, 4, 5, 6. Yeah, one of my students showed me that and it's genius. So I'm going to continue to use it.
You need
So
18.
yeah, so we use 6 and so we have 18 left, right? 18 left. So I'm just going to start putting them around. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18. Okay, so let's have a look at this. So first, when you make a, what you want to do is basically limit the total amount of charge as much as you possibly can. So we're going to look and see how much charge this particular structure gives us. So let's have a look. What would be the charge on each of the oxygens in this particular structure? Think about how many valence electrons oxygen should have, which is 6. Oxygen should have 6 valence electrons. How many valence electrons does oxygen have there?
8.
Nope, has 8 total.
7.
7, right. It has these two, these two, these two. So that's 6 that it keeps for itself. And when we're counting valence electrons, we also count one of the electrons that it's sharing. So it's sharing that 1 for a total of 7. So we take the number of valence electrons it should have and we subtract the number of valence electrons it does have, and that gives us a charge. So what's the charge on oxygen?
-1.
-1, that's right. So this oxygen is going to be -1. This oxygen is going to be -1. And so is this one because they're all the same, right? So that's a problem. Let's look at sulfur. How many valence electrons should sulfur have?
6, but it only has 3.
That's right. It has 6 valence electrons, just like oxygen, but it's only got 1, 2, 3. So that's a problem. So -3. So what's the charge on sulfur?
-3.
Nope, 6 minus 3. What does that give you?
3. +3.
+3, that's right. So we have a bizarre structure here where we have 3 negative charges and 3 positive charges. That's not going to be stable, is it? Because as we showed in class yesterday, electrons are negatively charged, and they're going to go from a place that has a negative charge to somewhere that has a positive charge. That's what electrons do. They move away from an area that has the same charge as they do and towards an area that is the opposite of the charge that they do. That's what charges want to do. Move from, if they're moved from where the similar charge is to where the opposite charge is. So what's going to happen is that, erase some of these. Erase that. Okay. I'll put that electron back. What will happen in this instance is
What do the oxygens have to share, right?
that's right. That's right. So a pair of electrons from each oxygen is going to move toward the sulfur to balance those charges out, because sulfur needs 3 more electrons and each oxygen has 1 more than it's supposed to. So what will happen is that each one of them will move a pair of electrons toward sulfur. And when it does that, we'll see this. So S, O, O, O. Now don't be freaked out when I show you this. 1, 2, 3, 4, 5, 6. I'll explain. 1, 2, 3, 4. Now, when each pair of electrons from each oxygen move toward the sulfur, they form another bond. So basically what this pair of electrons did here is form this. And this pair of electrons here formed that. And this pair of electrons here, you get the idea. Each one of them formed another bond. So how many valence electrons does oxygen have now?
4.
Nope. Valence electrons.
Oh.
And it has 4 lone pairs. Yes, it has 4 electrons to itself. It has this lone pair and this lone pair. So that's 4, but it's also sharing 1, 2, for a total of 6. So does this oxygen have a charge?
No.
No. So the charge in this oxygen is 0, the charge in this oxygen is 0, and the charge of this oxygen is 0. So that part seems fine, right? What seems wrong about this?
The sulfur can only have 8. You have
That's right. So that is a problem. And something we're going to learn tonight is that only atoms in group 2 or period 2 are stuck with the octet rule of having 8 electrons. And why? Because in group 2, you've only got S and P, right? You've got 2S and 2P. And how many electrons can you put in total into 2S and 2P? Oh man, you've forgotten your electrons already? How many total electrons can we put in shell number 2 that has 2S and 2P? Because we know those are the only 2 subshells in shell number 2.
18.
8.
8, yes. 1, 2, 3, 4, 5, 6. I put these in the wrong order. 7, 8. So total of 8 electrons. So oxygen is in period 2. It can only have 8 total electrons in its outermost shell. Same with fluorine, same with nitrogen, same with carbon, same with neon. They could only have a total of 8. But sulfur is in period 3. So it has the 3rd subshell. So what does that mean when it has that third shell?
You can
How
have
many total electrons can sulfur put in its outermost shell? So with sulfur, N equals 3. So how many subshells is that?
3.
3. What are they? There's 3S,
P.
3P, and
3D.
3D. You see, this is the key. Now I have room for how many electrons total? How many total electrons could sulfur put in its outer shell?
17.
Well, it's not going to be an odd number.
Sorry.
You're close.
18.
One more, 18. Yes, it can put 2 into S. It can put 6 into P. And remember, D holds 10. So sulfur can actually put 18 electrons in its outermost shell if it absolutely had to, because it has a D orbital in the 3rd period. So it can put a lot more electrons. And so sulfur, and as we'll see later, sulfur and phosphorus in particular do not have to follow the octet rule. They can put more electrons and form more bonds than period 2 elements can. And we'll see this all the time because sulfur and phosphorus generally, like when we look at phosphate ions and sulfate ions, what those are is sulfur and phosphorus in the middle of a molecule surrounded by oxygens, and they can form a lot more than 4 bonds. So here we have sulfur forming 6 bonds, but how many valence electrons does sulfur have? 6. It still has 6. 1, 2, 3, 4, 5, 6. So it still has 6 valence electrons, so its charge is 0. The fact that it can form 6 bonds seems a little weird at first, but it's not so weird because it has 6 valence electrons. Why can't it form 6 bonds? It doesn't, because it doesn't have any lone pairs. And so if it doesn't have any lone pairs and it's sharing its 6 valence electrons, that's fine. So remember, group 3, and specifically, well, not specifically, but a lot of times when you see sulfur or phosphorus in a molecule, suspect that they're going to have more than 4 bonds because they can, because they have a d orbital that can put these extra electrons in. Because here we see the sulfur's got a total of 12 electrons, right? Well, it's got room for 18. So that shouldn't be terribly surprising. It just looks a little weird to us because we've sort of been used to looking at, when we looked at the dot structures, the Lewis dot structures, we would say that, you know, because sulfur looks like this. So here's sulfur, and let me get so here's my dots. So we go 1, 2, 3, 4, 5, 6. So all the other elements, we say, okay, it's got this lone pair and this lone pair. It makes 1, 2 bonds. But since sulfur's electrons are further away, it's easier for it to break up these pairs and form more bonds. Oxygen doesn't like to do that because oxygen's lone pairs are close and it's more electronegative. It likes to keep those lone pairs close to it. Sulfur's less electronegative, and so those electrons are further away and they're not held as tightly. Same with phosphorus. Those electrons aren't held nearly as tightly, and so they're more prone to be shared, okay? So let's go back. I'll just erase all this crazy stuff. And let's fill in. So we got 24. This is our Lewis structure. So regions of electron density. How many regions, if we go around the sulfur, how many places does it have electrons around it? Remember, bonds are just regions of electrons. Doesn't matter if it's a single bond or a double or a triple. It's just a region where electrons are. So how many regions have electrons in them surrounding the sulfur? Here's 1. I'll give you a hint. Here's 1 right there. How many more are there?
Professor, quick question. On the Lewis structure, you want us to draw the final product instead of the first one we did?
Instead of the first one you did. What do you mean?
Like how we got this shape, like.
Oh, yes. Yeah. The final structure. And I want you to have the lone pairs in there too. So you should have these.
Oh, okay.
Yeah. Because the lone pairs will be very important when we talk about shapes. So how many regions of density where electrons are surrounding the sulfur? Someone just take a guess.
There are 3.
3, exactly. 1, that's 1, that's 2, that's 3. 3 different regions where electron density is high. And so where there are bonds, there's going to be electron density. Or where there's lone pairs, there's going to be electron density. Well, sulfur doesn't have any lone pairs in this particular structure. So the only regions of electron density are the bonds. And a single bond and a double bond, basically they're in the same space. And so we just consider it one region of density. So there's 3. So we have a look.
Like the region, it depends also the number for the other atom, like SO3, because I have O3, that's mean the region is gonna be 3, or no, it doesn't, it's not that way.
Sorry, could you repeat that?
I said in order to get the region, can I just like think about SO3? Oh, it has a 3, that's why we have a 3 region, or no? It's
No,
not that the region?
because no. Let's look at water. Water has 4 regions of density. 1, 2, this pair of electrons and this pair of electrons for 4. So we have to count up all the regions of. So it's more than just bonds. It's bonds plus lone pairs.
Okay, got you.
So this has 3 regions where there's bonds, plus 0 lone pairs for a total of 3. So, so later on tonight, I'll show you which molecular geometry we're talking about. But basically, what we have is 3 bonding regions and no lone pairs. So we would give it this particular. So we call it this kind of molecule. We say it has A, we just call that for the central axis, we just call it A. X is the number of bonds, and E is the number of lone pairs. So AX has 3 regions of bonding and 0 lone pairs. So we would say that this is AX3, and we'll look up. Actually, I can show you. Let me show you.
That's a quick question.
Yeah.
How come it's 0 lone pair? Are we not counting?
Because sulfur doesn't. Because we're talking about the central atom.
Oh.
Yeah, we're talking about the central atom. Here we go. All right. So can everyone see this? This is where we're. This is a slide from tonight's lecture. Okay. Can you see it?
Mm-hmm.
Yes.
Okay. So basically, we're talking about regions that have 2, or molecules that have 2 regions of electron density, ones that have 3 regions of electron density, and ones that have 4 regions of electron density. Okay? So our particular molecule is, as I mentioned, was AX3. So it has 3 regions of density and no lone pairs. So that's AX3, and that is called trigonal planar. Now you will not have to memorize these. You'll be able to look at this, at the slides. Okay, so you don't have to memorize it. But it sort of makes sense that if you have 2 regions, that's going to be linear, right? If you have 3, it's going to be in a triangle. And if you have 4, it's going to be in a tetrahedral shape. Because as I mentioned, electrons are negative. They don't like being close to each other. So they will move away to create the greatest distance they can apart from each other to reduce the electron charge repulsion. So if I have 3 regions where electrons are, they will arrange themselves into a triangle with 120-degree angles to maximize the distance between them. So when we go back and have a look at what that means for our molecule. Oh man, it erased all my.
I have a quick question. What does
Yeah.
the A stand for?
I'm sorry?
What was the A standing for?
Oh, A stands for the central atom. So A just stands for central atom. Or you could call it the axis if you want to. That's another way I remember it. So A is the axis of the molecule, the sort of the center of it. X is the number of bonding regions, and E is the number of lone pairs that the central atom has. So if you remember, we had O. So we have 3 regions of electron density. So because it's 3, we call it planar, triagonal. It's got 3 bonding regions, no lone pairs. That is a planar triagonal trigonal, whatever you want to call it, shape. Now, the really important thing to take away from this is this molecule going to be polar or nonpolar? Now, think about what does a molecule need to have to be polar? It needs two things, right? What's the first thing that a molecule has to have in order for it to be polar?
It has to be angular. It can't be symmetrical.
That's the first. Yeah, well, actually that's the second, but yeah, that's definitely one of them. Yeah, it can't be symmetrical. It's got to have some asymmetries to it so that it's different on one side than on the other. So the fact that this is a planar, it's triangular, all of these bond angles are the same. They're all going to be 120 degrees. Is this going to be a polar or nonpolar molecule?
Is it non-polar?
It's going to be nonpolar, right? So the two things that a polar molecule has to have is, one, got to have polar bonds in it. That kind of goes without saying. If it doesn't have polar bonds, then it's going to have trouble being even if it's asymmetrical, if they're all nonpolar bonds, it's still going to be relatively nonpolar. And sulfur-oxygen bonds are, I think, qualify as polar. I think the difference in electronegativity is greater than 0.4, although I'll have to check that. But it's asymmetrical. It's symmetrical, so already that eliminates it. It can't be polar if it's symmetrical. Because even if those bonds are polar, they're all pointing exactly away from each other. And when you add them all together, they cancel each other out. So we're going to do more of these tonight. I just sort of wanted to introduce how we take our Lewis structure and then turn that into a shape. So if it has 3 regions of electron density, it's triangular. If it has 2 regions of density, it's linear. If it has 4 regions, it's pyramidal. And then we get into all kinds of bizarre shapes with 5 and 6 regions. Okay? That's a lot to take in, but well, believe me, we'll do more of these. All right, who wants to, where do we go from here? Go to 2, 3, 4, 5. What would you like to do?
Do any example from 2, like just to practice from each question, one part.
Sure,
Yeah.
let's just look at C and D. We'll just compare C and D. So C, I've got nickel and or nitrogen and chlorine, and D, I've got cobalt and bromine. So, which are ionic and which are covalent based on where they are in the periodic table. Now, if I have nitrogen and chlorine, where are they on the periodic table? Are they metals or nonmetals?
N is metal
Non-metals.
and Cl.
Which, are they both metals?
Yeah.
Non-metals. Non-metal.
They're both nonmetals, right? They're both on the right side of the table. They're both nonmetals. So if I have 2 nonmetals forming a compound, what kind of compound is it going to be?
Covalent.
It's going to be covalent, that's right. You can also go to that website I showed you, ptable.com, which is a great place to go because it has the periodic table, and you just click on properties and it gives you all of the electronegativities. So I just basically just have that open on my desktop most of the time because I'm a nerd and don't have a lot of friends. So I like looking at the periodic table. So that basically will give you all the electronegativities. And if you remember, if the difference in electronegativity is higher than around 1.8, it's going to be ionic. And if you have 1.6 or lower, it's going to be covalent, okay? But just based on where things are in the periodic table, we don't even really need to know what their electronegativities are because we know the difference between metals and nonmetals. So this one is going to be covalent because they're two nonmetals. Now, what about cobalt and what do we call that? What would we call that? Since it's a covalent compound, what do we call it? You're going to have to name these.
What do you mean? What do you call it?
What do we call that in Cl3? What do we call it? What's the name of that molecule?
Oh, nitrogen trichloride.
That's right. Nitrogen trichloride. Because it's covalent, you have to spell out exactly how many atoms are there. Because as we've seen, like especially with like sulfur and oxygen, phosphorus and that, they can form all kinds of crazy bonds. So we don't know how it's organized. So by giving us the name, we know exactly how this is organized. And we could also, actually, what if for grins and giggles, we could draw the shape of that as well. So we'll do that after. So what about this one? It's got cobalt and bromine in it. So look on the periodic table, and where are they on the periodic table?
Ionic.
How do we know that?
Cobalt is a transition metal.
That's right, cobalt's a transition metal. So that tells us, so we have a metal, and bromine's just below chlorine in period 7. It's about as non-metallic as it gets, so that's a non-metal. So you have a metal and a non-metal together, that's equals ionic. So cobalt is going to, what's going to be the charge on cobalt here?
+2.
+2, right, because bromine is in group 7. It's a halogen. All the halogens in group 7 need one more electron to get to chemical nirvana, which is group 8. So it needs one more electron. So bromine is going to be -1, always -1. And since there's 2 of them and only one cobalt, cobalt has to be +2 in order to balance out the 2 charges from the 2 bromines, right? So what do we call that? What's the name of this compound?
Ionic?
We know it's ionic, but what's the name of the compound? If I needed that compound for an experiment, I told you to go to the stock room and get me what? I wouldn't say go get me some ionic.
Cobalt, Roman numeral 2 bromide.
Excellent, that's right, because it's a transition metal. Sometimes it's +2, sometimes it has other charges. And so if you just say cobalt bromide, I still don't know what you mean, because it could be COBr2, it could be CRBr3, COBr4, I don't know. So we say, yes, cobalt or cablat. Man, I can spell. Cobalt, cobalt. All right, cobalt. Here we go. Cobalt. Yes, 2 bromide. That gives you all the information you need. It's not cobalt. It's, oh God, cobalt. That's sad. Cobalt. A. Man, I obviously didn't get enough sleep last night, but you can see I'm a crappy speller. One of the reasons I married my wife, she could spell for both of us. Okay, I'm going to go back to this and show you how we would draw this particular, because I think it's instructive. So I've got N, and I've got 3. I got nitrogen. I got 3 chlorines. So I put, which one's going to go in the middle?
And nitrogen?
Yeah, nitrogen. Nitrogen, yeah, will go in the middle because it's less electronegative than chlorine. Not by much, but it is. The other reason is that nitrogen forms more bonds than, how many bonds can chlorine make? Or does it usually make?
3?
Chlorine?
Hold on.
Let's look at chlorine. How many,
Only makes one bond.
it makes one because, yeah, it has, how many valence electrons does chlorine have?
-1.
Nope. How many total outer shell electrons? How many valence electrons does it have?
7.
7, right. So you 1, 2, 3, 4, 5, 6, 7. So it has 1, 2, 3. Remember, it's highly electronegative. So it has 3 lone pairs that it keeps for itself, and it makes one bond. Nitrogen, on the other hand, has how many valence electrons?
5.
5, right. 1, 2, 3, 4, 5. So it has this lone pair. Now, nitrogen's very electronegative too. So it has this lone pair that it keeps for itself, and then 1, 2, 3 bonds. Now, what period are both nitrogen and chlorine in? Remember, period is just going across the periodic table. What period is it in? Are they both in?
Nitrogen is in period.
Actually, nitrogen is in a different period. I'm sorry. So nitrogen, since it's in the middle, we're sort of more worried about that. What period is nitrogen in?
2.
2. So how many total electrons can we put in its outer shell?
8.
8. So nitrogen has to obey the octet rule. Has to, because there's no place for it to put extra electrons. Yeah, chlorine is in group 3. So if we could steal those electrons away from it, it could form more, it could have more than 8 electrons in its outermost shell, but it really only needs that 1. So let's go back and start drawing. Yeah, question.
Is it after period 2? It doesn't have to be the octet rule.
Right. Yeah. Yeah. So once we get down to period 3, where we have S, P, and D shells, there's more places to stuff electrons. So sulfur, phosphorus, silicon can have more than 8 electrons involved in bonding. Okay. But now this will be easier because nitrogen can't do that. So we only have to worry about nitrogen having 8 electrons. So we put that in the middle and put our 1, 2, 3 chlorines around it. And we put 1, 2, 3 bonds to get started. So how many total electrons are we going to have in this particular molecule? Total valence electrons. So we already said chlorine's got 7.
26.
Wow, you did it fast. So chlorine has 7 plus times 3 for a total of 21. And you already did the math that nitrogen is 5. Total of 26. So how many electrons do we have left? So there's a total of 26. How many do we have to put in our
20.
20, right, because we've used 2 here. 1, 2, 3, 4, 5, 6. So we've used 6, so we have 20 left to put in. Let's just put them in. So 1, 2, 3, 4, 5, 6, 7, 8. And we always start on the outside. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Oh, I got 2 left. 20. So let's have a look and see if this makes sense. So each chlorine has how many valence electrons in that particular molecule? How many valence electrons does chlorine have?
7.
7, right. It has 2, 4, 6, 7. So it's claiming 7 electrons. It can claim 7 electrons for itself and just itself. It can also claim this one that it's sharing for a total. But it's these first 7. Whoops. Keep doing that. But it can claim those 7 as its valence electrons. So what's going to be the charge on chlorine?
No charge.
No charge. None there, none there, none there, because they're all the same. Now, what about nitrogen? How many valence electrons does nitrogen have here?
5.
5. 2, 3, 4, 5. How many valence electrons should nitrogen have?
5.
5. So what's the charge on nitrogen?
No charge.
No charge. So we have a stable molecule here. There's no charges on anybody. And everybody is the right, so therefore everyone has the right number of valence electrons. And everyone has the right total, because chlorine has 2, 4, 6, and a bond for 8. Nitrogen has 2, this bond 4, this bond 6, this bond 8. So they all have the right number of valence electrons. They all have 8 electrons. Everybody's happy. Now, what I'm interested in is what shape will this be? What shape will this look like? So I have nitrogen, and it's got pair of valence electrons, and 1 chlorine. I'll leave out the extra lone pairs on chlorine. So I just want to look at the shape. Now, how many electron regions, how many regions of electron density surround nitrogen?
3.
You're missing one.
4.
4, you're missing one. You got this bond is 1, this bond is 2, this bond is 3, and this lone pair is 4. That's where the lone pairs are essential to the shapes of molecules. And this demonstrates it very nicely, which is why I kind of wanted to do it. So 4 regions means it's tetrahedral. Even though, if we look at it, we go NCl3, well, that's 3 chlorines surrounding a nitrogen. That should be triangular, right? Just like the sulfur trioxide we did. It should look like this. And everybody be in a plane and everybody have an angle of 120 degrees. But it's not. And the reason it's not is because of this lone pair. That screws up everything. So basically, this turns it into a tetrahedral shape. And so the way we would draw it is, so we would have our nitrogen, and we have 1 chlorine coming out of the screen, looking like that. We sort of draw a wedge to show that it's coming out at us. That chlorine, and then we have, when we have this checked line, it means it's sort of going into the background. And that's where our lone pair is. And so we basically, each one of these angles is now closer to 109 rather than 120. And it's not all in one plane either. It's 3-dimensional now. So we have something coming out at us and something going away from us. And so so we call this triagonal pyramidal, because it looks like, and with chlorine sort of down and this on the top. So it kind of looks like a triangle because it's got these 3 chlorine atoms below the nitrogen and this lone pair of electrons on top. So we call that triagonal pyramidal. Now, is this going to be polar or non-polar?
Polar.
Yes, it's going to be polar because we have 2 different regions now that look different. We have a top that just has a lone pair of electrons, and we have a bottom that has 3 chlorine atoms. So it's going to be quite polar, actually. There's going to be a big difference in the electron density between the top and the bottom. And so we're going to talk more about this tonight, but I sort of just wanted to sort of give you an introduction as to the lone pair on the central atom of molecules is really important for determining the shape of it, okay? So for this question, you basically just need to find out where they are in the periodic table. If it's 2 nonmetals, it's going to be covalent. If it's a metal and non-metal, it's going to be ionic. You can also look up the electronegativities if you want. All right, who's got the next question? I'm dying to draw some more. That's what I like this chapter because there's not much math in it, right? The math is very easy. It's more just drawing things. Even though I can't draw worth a damn, I just like thinking about the way these things look.
Do example from question 3.
Okay, so these are third period. So what does that mean? Third. So both M and X represent elements in the third period. What does that mean? Where am I going to find the third period of the periodic table? Is that a row or a column?
Row.
It's row, right, exactly. It's the third one down. So it starts with sodium and goes across to argon, okay? It's the third period, meaning there's no transition metals. So if there's a plus, so if there's an element with a plus sign and an element with a negative sign, what kind of compounds are we talking about here? Are these covalent compounds or ionic compounds?
Is the M2 M with the 2 plus, is that periodic symbol or?
No, that's M and X represent elements. So M plus represents some element that has a charge of 2 plus, and X represents some element that has a charge of 2 minus or 1 minus or whatever.
So
So,
that the first one, A, would that be magnesium?
so let's see. Magnesium is in the third period, and magnesium has a 2 plus charge. You're absolutely right. So that would be magnesium. What would the X with minus 2? What would have a minus 2 charge in group 3? The third period, sorry, period 3.
Would it be zinc or no?
What's the charge on zinc? Well, actually, zinc is in, where is zinc? Zinc. Zinc's in period 4.
Sulfur.
And what charge does zinc, is a metal or a non-metal?
Transition metal?
It's a metal. So would it ever be negatively charged?
No.
No. So we're looking for a non-metal, right? We're looking for a non-metal in the third period that would have a charge of minus 2 when it forms an ion.
Is
Sulfur.
it sulfur?
Sulfur, right. Sulfur is in the third period, but it's in group number 6, right? Just below oxygen. And so we know that oxygen takes on a minus 2 charge when it's an oxide. So sulfur is just below it on the periodic table, and we've learned that elements below each other in the periodic table have similar chemical characteristics. So it also has a minus 2 charge. So what would be the formula for this compound? Basically, oh, go ahead.
Mg2s?
Mg2s. Is that balance? Balance the charges out. What's the charge on magnesium?
Sorry, it's just MgS.
Right, because magnesium is plus 2 and sulfur is minus 2. So there's 1 atom of magnesium for every 1 atom of sulfur. So the charge balances. And what will we call that? What would be the name of that compound?
Magnesium sulfide.
Mm-hmm. Why not magnesium 2 sulfide?
Uh,
Both are one.
Hmm?
Both are one, like we do not have now two. Why I will use dye?
No, I'm saying why don't we call it magnesium 2 sulfide?
because magnesium is a nonmetal.
No, magnesium's a metal. It's about as
Because
far
it's
to the
not a
left.
transition metal.
It's not a transition metal. There you go. Yeah, magnesium's way a metal. It's way to the left of the periodic table. It's about as metallic as it gets. But it always makes a +2 charge. Always, 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 because it's in group 2 and it's not a transition metal. So it's never any other charge. It's always +2. So we just say magnesium sulfide. And we know because magnesium's always +2 and sulfide's always -2, it's got to be MgS. It can't be anything else. So let's do the last one. So this tells us we've got a metal with a +3 charge, and we've got a non-metal with a -2 charge. And so the formula is M2X3. So what, and remember, M and X are both in the third period. So what could that be? What metal is +3 in the third period?
Aluminum.
That's right, aluminum. Aluminum is always +3. And we already know what non-metal is always -2. We just did it.
Magnesium.
Magnesium is the metal, which is +2. I'm asking which non-metal is -2.
Sulfur. Sulfur.
Right, sulfur. We just did it. So this would be a compound of aluminum and sulfide ion. So how would we write that? How do we write that as a formula?
Al2S3.
Right. So I have 6 positive charges here, and I have 6 minus charges there. And what would I call it? What name would I give it?
Aluminum. Then
Aluminum?
Mhm.
Aluminum what? Aluminum 3 sulfide?
I think so.
Okay. Is that right?
Is it aluminum trisulfide?
Okay. Aluminum 3 trisulfide? When do we use tri? Do we use that in ionic compounds?
We use it for covalent.
Yeah, we only use it for covalent compounds, so we can't have that. What about aluminum 3 sulfide? Is that correct?
Oh,
No, because aluminum also is not a transition metal. It's always +3. So we do not have that either. We would just call it aluminum sulfide. And then you would have to, just hearing the name aluminum sulfide, you would know that aluminum's +3, sulfur's -2, sulfide, then take the 2 and the 3. So you would know what the formula was just by the name. Okay. You want to do one of these?
can we do D?
D, okay. That one's going to be easy. D's going to be, D's going to be easy. D will be a little trickier, but sure.
Can we do E then? You said E. Which one was trickier?
I said D is going to be a little more difficult. P's
Yeah.
pretty, B's pretty straightforward.
Oh no, I was talking about D.
Oh, D, this one. That one?
Yes.
Okay. All right. Yeah, cool. Let's do that one. So how many first, which one's going in the middle?
P.
Yeah, if anything with fluorine, fluorine is going to be on the outside, looking in. So we have phosphorus, and we have 1, 2, 3, 4, 5, 6 fluorines. Dang, that's a lot of fluorines. Okay, so let me move this one a little bit. Fluorine. Okay, and here's my electrons. 1, 2, 5, 6, 7, 8, 9, 10, 11, 12. All right, so how many, and already you can see that phosphorus is violating the octet rule like a mother, right? I mean, it's forming 6 bonds. So already that's problematic because it's got 12 electrons, but not a problem because it's not in group 2. Sorry, it's not in the second period, it's in the third. So it has S, P, and D. So it has room for those extra electrons. So we don't have to freak out about phosphorus having more than 4 bonds. It often does. So how many total electrons are we going to have here? So phosphorus is how many?
Phosphorus has 5.
5 valence electrons. And fluorine, by God, you got to know this by now. How many valence electrons does fluorine have?
7.
7. Yeah, it does. And there's 6 of them, so dang, that's a lot of electrons.
42.
That's 42. So we have 5 and 42, 47. And I already hear someone saying
Plus 1, so 48.
+1, right? Always remember to take into consideration the charge. Now, if it was plus, we'd take 1 away and have 46. But since it's negative, we add 1 and have 47. Because you'll find that almost always the total number of electrons is going to be even. Like I said, because even number of electrons is stable. You have an odd number of electrons that tends to leave shells or orbitals unfilled. And so you have single electrons, and they're very, very reactive. They don't, and will react with things. So a molecule wants to achieve stability. It's exactly why it becomes a molecule, to achieve stability. So it usually is an even number of electrons. So 48, dang, we're gonna have to put a lot of them in here. All right, so remember, we always start going around the outside. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. So 36. Oh, right. How many electrons are we supposed to have? So it's 48 minus
12.
minus 12. So how many should we have total that we just put in? We have 12 in bonds. We have 48 electrons. We have
36.
12 of them in bonds and 36. And how many did I just put in there? I put 6 on each fluorine, and there's 6 of them, so that's
36.
36. Let's have a look. So let's check and see if everybody's happy. So each fluorine has how many valence electrons?
7.
7, that's right. They each, so we have 2, 4, 6, and that 1 for a total of 7. And we subtract the number of valence electrons it should have, which is 7 and 0. Now, phosphorus, what's the charge? How many valence electrons should phosphorus have?
5.
Should have 5 valence electrons. Let's see how many does it actually have?
6.
It has 6 here. It has 1, 2, 3, 4, 5, 6. 6 valence electrons. So what's the charge on phosphorus?
-1.
-1. Right. So this structure, so we say this whole structure has a charge of -1. We just put a big bracket around it and say -1. But you can see where that negative charge is going to be. It's going to be on the phosphorus, because it should have 5 valence electrons, but it actually has 6. What's the total number of electrons that phosphorus has? So it has 6 valence electrons in the structure. How many total electrons does it have? It has 12. Right. Is that an issue?
How is it 12?
It's got 2, 4,
Ah,
6,
okay.
8, 10, 12. So the valence electrons are basically 1/2 of the electrons in a bond. So 1/2 of the bonding electrons are valence electrons, because each atom could claim one of those the bonding electrons as theirs, because they brought that to the table. So fluorine is donating one of its valence electrons. So if I have a phosphorus fluorine bond, that electron on the left closest to phosphorus brought that to the party. And the electron closest to fluorine, well, fluorine brought that to the party. They're sharing both of them. So they can claim 2 for the total, but they only claim the one closest to them as a valence electron. So when we're counting valence electrons, we take half the number of bonding electrons and we add the number of lone electrons or lone pair electrons. So that's why fluorine has 2, 4, 6, has 6 lone pair electrons, and it has 1 electron per bond. So it has 7 total. So the fluorines don't have any charge, and you can see the fluorine pretty much always has 6 electrons and a bond. It pretty much always has that, because it's so electronegative. It does not share any of its lone pair electrons, like basically ever, and it just shares that one, so it can fill up its shell. And phosphorus has 12 total electrons, but that's fine because it has room for 18, as we saw, because it has an S, a P, and a D subshells in its outermost shell. All right, is there one more of these you wanted to do on the next page? I'm going to pick one.
Can we do H?
Sure. Yeah, you can see the difference here between sulfur trioxide and what's this? Oops, let me go back. This isn't sulfur trioxide, is it? What is this? Because we did SO3 already.
Sulfite?
Right, this is not sulfur trioxide. This is sulfite, ion. That's a different thing. It's going to have a different structure as well. So we'll start with who's going to be in the middle.
S.
Yep. Sulfur pretty much always gets stuck in the middle. And we'll put the 1, 2, 3 oxygens around it with 1, 2, 3 bonds. Okay. So how many electrons total?
24.
S has 6, oxygen has 6, and there's 3 of them, so 24. I think you're missing something.
The 2 plus, so you have to add 2 more. So
It's 2 minus, so it's 2, it means 2 more electrons. Right, so we add those 2. So now we have 26 electrons. Now how many electrons do we have in bonds already?
6.
6. So those are the electrons we have in bonds. Now remember, this one is a sulfur valence electron. This one is an oxygen valence electron. Oxygen valence, sulfur valence, oxygen valence. Okay, that's how we count the number of valence electrons. So we have, so there's 6 electrons in bonds, 2 times 3, So we have a total of 20 electrons left over. So as usual, we go around the outside.
Professor, just a quick
Yeah.
question. So you said 24 total. How do you get the extra 2?
It's got a -2 charge. It's an
Ah,
ion. It's an ion with 2 more electrons. We have to put those. We have to put those in the molecule. They got to go somewhere. Now we're going to figure out where they go. All right. So total of 26. And we have 6 electrons in bonds, meaning we have 20 electrons left to play with. So let's start putting them on. So I'll change the color just because it's fun. All right, so 2, 4, 6, 8, 10, 12, 14, 16, 18. Well, I got 2 left. Where do they go? I have 2 electrons left. Where do I put them?
Sulfur on top.
Yeah, I put them in the middle. Anytime you have electrons left over after you've decorated all the atoms around the outside, you put them in the middle. So sulfur gets a lone pair. So that's all of our electrons. Now, so you do that first. What's the next step? After you do that, what do you do next?
You check their valence electrons.
Yep, you check their valence electrons. That's a good thing. That's a good place to start. Because by checking the valence electrons, we check and see what the charge is of each atom. Because if it has too many valence electrons, it's going to be negatively charged. If it has too few, it's going to be positively charged. Now we know how many valence electrons should both oxygen and sulfur have.
6.
They should have 6. So let's see. So all 3 oxygens are the same. So it's how many valence electrons do the oxygens have?
7.
7. 2, 4, 6. And remember that half the bonding electrons are also valence electrons. So it's got a total of 7. So it should have 6 electrons, and we subtract the number it actually has, which is 7. So what's the charge on all 3 oxygens?
-1.
-1. So this one's going to be -1, that one's going to be -1, this one's going to be -1. Now we look at sulfur. Sulfur also should have 6 valence electrons. Let's see how many does it actually have.
Five.
It has 5. 2, 3, 4, 5. So we'll subtract the number of valence electrons it actually has. What's the charge on sulfur?
+1.
+1, that's right. So whenever we have a molecule that has a negative charge and a positive charge adjacent to each other, that's trouble. Because as I mentioned before, where do electrons like to go? From a place where it's negatively charged, just like they are, so that's repulsive. And it likes to go to a region where there's less electrical charge, where there's a positive charge. So it goes from the negative to the positive. So what's going to happen with this structure?
Double bonds.
We're going to get a double bond. One of these oxygens, and you can pick whatever one you want, one of those oxygens is going to donate a pair of these electrons. So a pair of these electrons is going to jump from the negative charged oxygen to the sulfur, because that's where they like to go. They like to go from the negative charge to the positive charge. And when it does that, it forms another bond. So now we get a double bond here. And these 2 electrons are no longer they're no longer valence electrons completely for the oxygen. Now, one of them becomes a valence electron for the sulfur, and the other one's retained as a valence electron for the oxygen. So the oxygen doesn't actually reduce the total number of electrons it has. It still has 8. It's just that it's reduced the amount of valence electrons by 1. So the total number is still 8, so that's still totally fine. now oxygen, left one here. So oxygen has 2, 4, 5, 6 valence electrons. So it now has no charge. This negative charge is now gone. But it still has 8 total. Because it still keeps, it can still count those, all the electrons in both bonds and lone pairs as electrons total. So it has 8 total, but it no longer has a charge. Now let's look at the number. Now sulfur has gained another valence electron. It now has
6.
2, 3, 4, 5, 6. It now has 6 valence electrons. And so its charge is now 0. So basically we've eliminated 2 charges. And what basically that's what you want to do when you're drawing these molecules. You want to reduce the total amount of charged atoms to the smallest number you possibly can. Because if you have like 6 charges in a molecule, that's going to be extremely unstable. And so what will happen is that electrons will move away from the negatively charged atoms to the positively charged ones and basically neutralize everything. So now sulfur has no charge, and it still has 2, 4, 6, 8 total electrons in its outer shell. So it's fine. So everybody's happy. But do we still have, now remember, you still should have a charge of -2 in the molecule. And do we have that?
No, we don't.
You sure?
I have the
Oxygen.
one.
The oxygens, we have it.
Yeah, these 2 options still are -1. This one and this one are still at -1. So you add them together and you get -2, which is what you want. This is an ion. It should have a net negative charge, and it does. So let me just sort of, because we got so much mess there, let's just basically draw it again. So this is what we've wind up with. So this oxygen is negatively charged. This oxygen is negatively charged. This sulfur is neutral, and so this sulfur has no charge, and this oxygen has no charge. So the total charge of the molecule has to be -2. So you can't get rid of all the charge because it's not a neutral molecule. There has to be charges in there. And the total number of charges, or the net charge of all the atoms in that molecule, has to equal the net charge in your formula. So the formula tells me it's got -2, and the diagram tells me it's got -1, -2. So that's correct. Now, can someone tell me whether or not, is this the only possible way of drawing this molecule?
No, you can have the double bond and another oxygen.
That's right. And just like we learned last, so the double bond could be here, or the double bond could be here. So you remember from last night where we sort of left off that all 3 of these are possible. And so we have what really looks like 1 1/3 bonds between each sulfur. Whoops, oxygen. And the negative charge is distributed evenly all around the outside. So all these bond angles are the same. All these bond lengths are the same. So yeah, we sort of left off with that last night. We'll pick it up there this evening, talking about how we look at these hybrid models. But yeah, if I don't ask for the hybrid model, just give me the double charge on one of the oxygens and single bonds, or double bond on one of the oxygens and single bonds on the two others. That's fine.
So I have a question.
Mm-hmm.
Whenever there's a plus charge and
Mm-hmm.
then charge, that's when you do a double bond.
Yes, if you have a negative charge right next to a positive charge, you're going to form a double bond, because it's, like I said, it's very unstable for it to be a positive and a negative charge right next to each other. It's positive. It's possible to have a positive and a negative charge in the same molecule. I'm not saying that happens all the time, but they're normally separated by a great distance, so that, you know, that lone pair of electrons just doesn't zip all the way over and negate that positive charge. But if they're right next to each other, those electrons are going to move to the middle.
It's hard.
It takes a while. This will take a while to work up. I don't know. I kind of like. I think it's fun. I like playing with the number of electrons and moving them around and seeing if it works out in the end. But, you know, I don't have a lot of hobbies. Okay. What do we want to do next? And have fun with phosphate. Phosphate, PO4 -3, is very similar to the sulfite. And what I should have put sulfate on here, because you see the sulfite is -2, and you'll see the sulfate is also -2, even though it's SO4. And so it's kind of interesting to draw SO3 next to SO4 and see that they can have exactly the same charge. Maybe I'll do that on a test or something. Anyway. So either everybody's like knows this like the back of their hand, or they're just so confused now they don't know what to do. One of those is correct, right?
Can we do the E on the back, the resonance form?
No. Of course we can do that. E. Okay, yeah, formate ion. Okay. Right, so we were just talking about resonance forms. So if I have carbon, oxygen, oxygen, hydrogen, and the whole thing, and somewhere in this we have a negative charge. So first thing we need to do is figure out how many total electrons am I going to have. So I've got a hydrogen. How many valence electrons does hydrogen have?
1.
Just 1. So hydrogen's got 1. Carbon's got
3. 3.
Sorry, what'd you say?
Carbon has 4.
4. Yeah, I thought you said. I heard 8. Sorry. Noble gases have 8 valence electrons. Carbon only's got 4. And oxygen has how many?
6.
2 times 6. So we got 5 and 12, 17.
Plus 1.
Ah, there you go. Plus 1, because it's got a negative charge. And you can see again, even number. If you get an odd number, there's something weird going on. So like sort of double check your math, because you should be getting an even number. Even if it's like you've got to add electrons or subtract electrons, because it's charged at the end, the number you should get should be even. So we got 18 electrons. So let's do our thing. So we'll start putting them in there. So how many electrons are in bonds? So I have 18 total here. How many are in bonds already?
3. So 6 electrons are in bonds.
Yes, 6 electrons are in bonds. Those are my 6 electrons. So minus 6. So I have 12 electrons to add. Okay, let's do that. So I got 12 to put in here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Done. So we've added our electrons. We don't have any left. What's our next step?
Count the valence electron.
Yes, we do. We count the valence electrons. So how many valence electrons should hydrogen have?
1.
1, and it's got 1. Got that sad little electron there. How many valence electrons should oxygen have?
6.
Should have 6. And how many does it have?
7.
It's got 7. 2, 4, 6, 7. Same with the other one. So what's the charge on both those oxygens?
-1.
Yeah, so this oxygen's -1, this oxygen's -1. And let's look at carbon. How many valence electrons should carbon have?
4.
4. And how many does it have?
3.
1, 2, 3. It's only got 3. Oh no. So what's the charge on carbon?
+1.
+1. Now, carbon really doesn't like to be charged. You very rarely see a charge on carbon. So carbon is positive. So basically we have an example right here of a molecule that has too many charges in it. It's got 2 negatively charged atoms, both connected to a positively charged atom. So what's gonna happen?
Double bond one of the oxygens.
Right. So one of these lone pairs from either one of these carbons, and that's the key to it being in resonance. Let's just pick this one. That'll go to the middle, form another bond, and so that lone pair will go away and be replaced with a bond with 1, 2 electrons in it. So now, what's the charge on that oxygen?
-1. Well,
It was -1. What is it now? How many valence? So it should have 6 valence electrons.
No charge.
And it has 2, 4, 5, 6.
no charge.
Doesn't have a charge anymore. And what about the carbon? How many valence electrons does it have?
4. So that has no charge.
Right. So this charge goes away as well. And so we're left with this oxygen, which we've done nothing to. And so it still has a charge of -1, which is what we want formate to have. Formate has a charge of -1. So this structure makes sense, okay? So let me clear that, make it a little more easy to read. So what we've got is this. And here's my 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So what is the other structure it could be?
The double bond on the other oxygen instead of the top oxygen.
Right. So what we would have is, and then our 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So each of these is equally plausible. So there's 2 ways to write the resonance structure. You just write it like this, that's fine, and say basically it goes back and forth between this structure and that structure, and they both have a -1 charge. Or you can also draw it like this. Like that. And then have a 1, 2, 3, 4, 1, 2, 3, 4. And then another pair sort of goes back and forth. We don't write it, but the other pair would basically be here and just sort of moving back and forth so that that charge is delocalized. That's what we call it. Remember, that's where we left off last night. It would be a delocalized charge, but we don't draw this. We just have that bond there as demonstrating there's sort of half a bond here. Wait a minute, I'll get a different color. There's half a bond there and half a bond there. So there's basically 1.5 bonds from carbon to each oxygen for a total of 3, and then 1 to hydrogen for a total of 4. So what do we say the bond order of these two bonds is? Where a single bond has a bond order of 1, a double bond, a bubble, damn dyslexia, double bond has a bond order of 2. What's the bond order of those two bonds?
3, 4.
Because it's more than a single, but it's not quite a double. Remember, it's the average, basically it's the average of a single and a double bond. So what would the bond order be?
1.5.
1.5, right. So we basically say that this is like a bond and a half here, this is a bond and a half here, and that's 1 bond there. So carbon has 4 bonds, which it should. Okay? Starting to make a little more sense, hopefully. When you get in there and start drawing them, just actually, because that's the way I learn. I don't learn by looking at things. I learn by like writing things down and playing with them and moving arrows around. That's how it's gonna like stick in your head. Having it demonstrated to you just goes over your head, and it's confusing. When you do it yourself, it'll make more sense. I promise. So we have a little more time left. Is there one more you want to try on?
Can you do T?
A of what?
Let's do D, as she said. It's okay.
These? Oh, selenium dioxide. That's basically going to look like ozone, which are in the slides. Oh yeah, there's phosphate. Man, I got phosphate twice. Carbonate. Oh yeah, do you want to do benzene then?
Yeah.
Yeah, benzene's a classic. Benzene is the molecule that is taught as having a resonance form. So yeah, it's also in organic chemistry. We call it one of the it's basically the basis of the aromatic compounds, because it's these bonds are so conserved that yeah, it has this particular odor to it. It's very aromatic. So we just draw the structure like it is there. C, 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 with an H on each one. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So hydrogens have 1 electron. I got 6 of them. How many does carbon have? Valence electrons.
Oh.
Just did carbon. How many valence electrons does carbon have?
3.
4.
4. It's in group 4. So we got 6 times 4 is 24. 6 times 1 is 6. So we have 30 bonds. 30 electrons. And how many electrons are in bonds? We've got 12 bonds. How many electrons in each bond? Come on.
26.
26? How many bonds do we have?
1, 2, 3, 4, 5, 6, 7, 8, 9,
12.
12, 24.
24.
So we have only 6 electrons left. Oh no, what are we going to do? So we only have 6 left. So, and we got, can we put any of them on hydrogen?
No, you can put it on carbon.
I can't put them on hydrogen, right? Because hydrogen only has 2, hydrogen already has 2 electrons. It's done. It can't hold anymore. And it has 1 valence electron, so it's not charged. So it's fine. How many valence electrons does each carbon have?
4.
4. And how many valence electrons does each of these carbons have in the diagram?
3.
3. Right. So what if I just put the pairs on every other carbon? So I put 2 here, and then 2 there, and then 2 there. Because remember, I put them on in pairs, right?
Oh, you have to put it as pairs. You can't just.
It helps. I mean, you can't put them one at a time, but you'll see the same thing will happen. Because remember, molecules do not like to have unpaired electrons. Unpaired electrons are extremely reactive. So if you have something with an unpaired electron, it basically will react with another unpaired electron and pair up. So we can do it both ways. The same thing will happen. So basically we have 2 different carbons. We have ones that have a lone pair and ones that don't. So the ones that do, how many valence electrons do they have?
The ones that have the lone
The ones
pair?
that have a lone pair, how many valence electrons do they wind up with?
5.
5, right. They have 1, 2, oh, whoops. Oh, this one, okay, let's look at the one that doesn't have a lone pair. I screwed up.
You have 3.
They have 3. So the ones that don't have a lone pair, how many valence electrons should carbon have?
4.
Should have 4 valence electrons. And the unpaired, the ones that don't have a lone pair only have 3. So they have a charge of +1. So +1, +1, +1. Now the ones that do have a lone pair have 2, 3, 4, 5 valence electrons. So they should have 4 valence electrons. We subtract the valence electrons they do have, and what's the charge on them?
1. -1.
-1. So we got a messed up situation here. We have a molecule where half the carbons have negative charges and half the carbons have positive charges, and they're right next to each other. That's not going to work, right? So what do you think is going to happen?
Gonna change the shape.
Not so much the shape.
Oh,
If you have electrons in a place where it's negatively charged, right next to a place where it's positively charged, where are those electrons going to go?
To the positively charged.
Yeah, they are. So what's going to happen is this lone pair is going to move here. So to that carbon as a positive charge. This lone pair is going to move here to where the positive charge is. And this lone pair is going to move there to where the positive charge is. So what are we going to be left with? We're going to form
Double bonds.
a double bond there, and a double bond here, and a double bond here. And these lone pairs will all disappear into bonds. So let me get my eraser. Yes, so this lone pair will go away. This lone pair will go away. This lone pair will go away. And basically all the charges will go away as well. So this is what we'll be left with. A double bond between these 2 carbons, a double bond between these 2 carbons, and a double bond between these 2 carbons. What else could have happened?
The double bond could be in the other opposite carbons.
Exactly. Instead of the double bond being here, the double bond could be there. And then this double bond moves here. And then this double bond moves there. So basically we just move the double bond one over. And where there was a double bond, now there's a single.
So for this question, would you want us to write both? Like the
yeah, so there's,
drawings?
right, so there's either this one, 1, 2, 3, so the double bonds are there, or if we look on the outside, the double bonds could be here, 1, 2, 3. There's no rhyme or reason that it has to be, they just have to be separated by 1. It just has to go single, double, single, double, single, double. Doesn't matter, or it could be double, single, double, single, double, single. It doesn't matter. There just has to be a double and then a single and a double and then a single and then a double and then a single. That's those. So those would be the two resonance structures, where it's double, single, and then where it's single, double, in that order. Okay, you see how that works? So if I have if we label them carbon 1, 2, 3, 4, 5, 6. Just means I have a double. If I have a double bond between 1 and 2, it means the next one's going to be between 3 and 4, and then the next one's going to be between 5 and 6, and the rest will be singles. Now, if I have a single bond between 1 and 2, that means 2 and 3 are going to be the double bond, and then 4 and 5 are going to be the double bond, and then 6 and 1 are going to be the double bond. It's just a single followed by a double, followed by a single, followed by a double, in whichever order you want. But neither of those is the accurate, that is, neither one of those is the accurate structure of benzene. It's what benzene, the way organic chemists draw it is like this. We leave out the hydrogens, we just assume they're there. So that would be a double, that would be a double, that would be a double. This would be a single. That's how organic chemists draw it. So they either draw it like this, or they draw it like this, with a circle in the middle, meaning that all of these bonds are equivalent. This one is the same as this one, the same as this one, the same as this one, same as this one, same as this one. And if you look at it, if you actually look at the bond lengths and the bond angles, they're all identical. Which says that this resonance structure is actually the real structure of benzene. It doesn't have single bonds and double bonds. It has bonds and a half all the way around. So basically these electrons going from here to here to here are constantly moving. And so it creates a structure that is not a single nor a double, it's somewhere in between. Right, was that too much for everybody? It's your first lesson in organic chemistry. Wasn't that fun? You get to see how real organic chemists write things. They leave out hydrogen because nobody cares about it. It's carbon, baby. That's all that matters in organic. Any questions about that? Yeah, there's two ways to write it. You can write the single double, and then with the arrow. So single double on this side, 1, 2, 3, and on the other side, the other one, 1, 2, 3. So that's in resonance. And then the other way of writing it is just to write it like that.
Can we do another example from the?
Sure, we'll do one more, and then we'll hit the road. I gotta squeeze the dogs. Okay, which one do you want to do?
Something has idea.
Anyone else have a suggestion? Is anyone left? There's still 19 of you here. You're being quiet, but I know you're still here. Or maybe just your computer's on, you've walked away from it, given up. Yeah, we'll do one more.
Let's do B,
B.
phosphate ion.
Oh, phosphate. Yeah, phosphate's a classic. Okay. Phosphate's fun. Phosphate. Yeah, violates the octet rule like a mug. Okay, here we go. So, let's do phosphate. Find a new color. I don't have enough colors here. I need more colors. All right, that's one kind of boring, but I'll go with it. Okay. So I have one phosphate, 4 oxygens. Which one's going in the middle?
Phosphate.
Phosphate's the whole thing. Which atom is going in the middle?
Phosphorus.
Phosphorus. There you go. So phosphorus goes in the middle. Actually, that's too light. It's orange. Let's try that one. So yeah, and then we have 1, 2, 3, 4 oxygens surrounding it. So 1, 2, 3, 4 bonds. Okay, so how many total valence electrons? So we have 1 phosphorus. How many valence electrons is that?
5.
5, right. And we have 4 oxygens, so that's 4 times how many?
6.
6. So 4 times 6, 24, plus 5, 29 electrons.
Plus 3.
Oh, right, plus 3 more. And notice we get an even number, right? 32, which is like, that should tell us something. That's what we want. We want an even number. Okay, so 32 electrons. How many are in bonds?
8.
8, right, we got 8 already in bonds, so it leaves us with 24. So we have 24 electrons. Let's fill out where they're gonna go. So I'm just gonna put 6 on each oxygen, right? I got 4 oxygens. I'm gonna put them around the outside. Each of them are gonna get 6. 2, 4, 6, 2, 4, 6, 2, 4, 6, 2, 4, 6. That's my 24. So I have no electrons left. So I have none to put in the middle. So as we've pointed out, we got our electrons done. So we're done with that part. Now we need to figure out what?
Valence electron.
Yeah, valence electrons and charges. I mean, they go together like cats and soup. Okay. So how many valence electrons? Oxygen should have how many? Now they're all the same, so we only need to count. Only need to count 1. So oxygen should have 6, right? Should have 6 valence electrons, Val-E's. And how many valence electrons does each oxygen have?
7.
7, right. It's got 1 for the bond, and it's got 2, 4, 6 for the lone electron. So it's a total of 7. So what's the charges on the oxygens?
It's going to be -1 on all of them.
On all of them, right. So -1, -1, -1, -1. All have a charge of -1. Oops, sorry, Jerome. They really want to go for a walk. They're right by my feet now. Yeah, so they're all -1. Now let's look at phosphorus.
It needs to have 5, so it's a +1 charge.
That's right. Man, you're way ahead of me. Yeah, phosphorus has 5 valence electrons. 5 Val-E's, but it's only got 4. 1, 2, 3, 4. Oops. So it's only got 4. So we subtract 4 and we get +1. So phosphorus is +1. So this is untenable, right? If we have negative charges next to positive charges, that's just not going to work. So what's going to happen?
1 double bond on the top oxygen.
Yeah, let's take this lone pair on this oxygen. Now it shares that lone pair with phosphorus and forms another bond. So now I have a double here, and I'll just subtract So this lone pair is gone. And that oxygen no longer is negatively charged, right? Because it has 2, 4, 5, 6 valence electrons, just like it should, and a total of 8. So that oxygen has no charge anymore and is totally zen. And the phosphorus now has 1, 2, 3, 4, 5 valence electrons. So it is now not positively charged either. So it's totally zen. So we've removed the negative charge and we've removed a positive charge while keeping the total number of electrons the same. So this is a more stable form of the molecule. However, we're still left with 3 charges. What do we do about those?
We put a parentheses over the molecule and the -3 on top.
Yeah, we and just put -3. But pretty much we know where those charges are, right? One of them's there, one of them's there, and one of them's there. But they're supposed to be there because they're negatively charged oxygens. And oxygen's more electronegative than phosphorus. So if someone's going to be stealing an electron from somebody, it's going to be oxygen's going to be keeping it. So that's basically where those 3 charges are going to be. Now, the resonance part comes in. How can this be a resonance structure?
Because the oxygen bonds could be interchangeable, the double bond.
Right, exactly. Because if this is oxygen number 1, and this is oxygen number 2, number 3, and number 4, there's no reason why oxygen number 1 has to have the double bond on it. It could be 2, or it could be 3, or it could be 4. It could be any one of them. So those are your 4 resonance structures, where the double bond is on 1, or the double bonds on 2, or on 3, or on 4. Those are and the other 3 are then have a single bond that are negatively charged. So you actually have 4 resonance forms for phosphate ion.
So do we have to show you all 4, or could we do that interchangeable thing?
Yeah, either one. I just generally draw all 4, but yeah, you don't have to. You can just draw if you want to draw the intermediate. Actually, because it says resonance forms, so it doesn't say resonance form. So I think yeah, so all 4 of them.
So we just have to put it on a different paper then?
So just you can, yeah, either put it on a different paper or yeah, make them really small. I mean, what you could do is just put the lone pair on one of them, and then just leave the lone pairs off the next 3. I mean, I pretty much get it. Because yeah, it's a pain putting in the lone pairs, especially if you're doing 4 of them. Because yeah, your finger starts to get numb after a while. But yeah, so just put the full structure on one of them, and then the next 3 just have, you know, that one, and then the next one, and the next one. Just leave the lone pairs off. That's fine. Because if you have the lone pairs in the first structure, I know you know where they go. You don't have to continuously show me where they go. I get it.
I have a question, Professor. In the exam, and also when I answer this recitation paper, because you drew a lot of steps, and I have to do also a lot of steps in the paper sheet. Do I need to write like what the steps that I'm doing to answer, or just you want the final?
Just the answer. Yeah, you can sketch out somewhere. Yeah, because you did show the whole thing, and like showing the electrons moving around. My God, your paper would fill up like super fast. So yeah, so on a piece of scrap paper, do your electrons moving around and getting it right, and then when it looks like it makes sense, then put it on the recitation. Yeah.
Okay. It will take time to do this homework.
Yeah, it does. Yeah, but it's through doing them this way that'll stick in your head. Because yeah, like I said, just having me doing it and showing you or reading it in a book, that's not going to stick. I need to write things down in order for me to remember anything.
So in the lecture, we will do the same practice, the one we do now, or different?
Yeah, well, tonight we're gonna sort of review again, like how to do these, but then sort of get more into the theory of how these particular diagrams lead to actual molecular shapes.
Okay.
And then, because there's no way to know whether these are polar or non-polar until you actually make it into a shape, because you need to know what the shape is before you can tell whether or not something's symmetrical or asymmetrical, right?
Okay.
All right. So, if there aren't any more questions, I will see you guys in a little while. Get something to eat or have a nap or do something. Walk your dogs. I'll talk to you soon. All right. All right. We'll see you in a little while.
Thank you. Bye.
All right. Thank you.